Hello friends. So far we have been extensively focused on the Carnot cycle, and there is a reason for it. Now in the previous lecture we arrived at a specific relation that we referred to as a critical one. Now the reason why we extensively consider the Carnot cycle, one of the reasons is to arrive at this specific relation. Now this lecture, let us begin by expressing or rewriting this relation. Now, if you could recollect, the Carnot cycle helps us theoretically represent the operation of an heat engine. So generally in heat engine, heat input is fed and this heat input is translated to work, and not all heat input is translated to work, some of the heat input is lost, and this lost heat input is something that we observe in the physical world, and all these different components that we observe in the physical world is rather expressed in the Carnot cycle by using rather simple, straightforward thermodynamic variables of pressure and volume. So that is one of the key features of the Carnot cycle. Now this Carnot cycle, in the previous lecture, it helped us understand or arrive at or define few specific parameters. So one such specific parameter was the efficiency, and this efficiency is nothing but the work done by the amount of energy input, the thermal energy input that we feed in, thermal energy input. Now in the previous lectures we have considered that this work done, if we treat it as W and the amount of thermal energy input as QIN, this work done is nothing but the difference between the amount of heat input that you have provided and the heat that is lost. So this expression or the relation or the description of the efficiency about this form, that is the heat input that you feed in and the heat input that is lost, divided by the amount of heat input that you feed in. So essentially it is the description of the work that allows us to describe the efficiency entirely based on heat input and the heat lost. So the work, if you could recollect, the operation of the heat engine, during the operation of the heat engine, some of the heat is lost, so therefore only a portion of the heat input is getting converted into work, so that needs to be included while describing the work that is done by the system. And one other area or one other fundamental concept that help us relate the work done to the heat transfer is that since we are able to quantify the heat that is lost during the operation of the heat engine, there is not much change in the internal energy, and therefore this rather constant internal energy, no change in the internal energy, allows us to relate the work directly to that of the heat that is involved, the heat transfer that is involved, which in the operation of heat engine is the difference between the heat input and the heat output. Now in the previous lecture we spent exclusively the session on deriving at a specific expression, that is the efficiency in the Carnot cycle, which again is the theoretical description of the operation of the heat engine, can be expressed using a state variable, that is the temperature of the reservoir that allows the heat transfer to occur. So you have the reservoir at high temperature and a reservoir at the low temperature, and when you consider the work done during the Carnot cycle and when you consider how this work done can be extensively expressed, just not in terms of the heat transfer but in its canonical description, we arrived at this expression in the previous lecture. So here what we have is the transfer of heat, here is the temperature of the reservoir. So if you could recollect, for our recollection, let me just revisit our Carnot cycle. What you have is the fundamental thermodynamic variables that are involved, and you start with a point A, and there is a heat transfer that is QIN that allows the system to move from state A to state B. So there is a transfer of heat QIN. This transfer of heat is due to a high temperature reservoir that is in contact with the system. So this high temperature reservoir is what allows the heat to transfer, and because of this heat transfer the system moves from state A to state B, and there is an equilibration process that occurs and the system moves from B to C, and now the system is in contact with low temperature reservoir. This allows the heat that is lost during the operation of the heat engine to be transferred to the low temperature reservoir. So therefore the system moves to a new state D, and in order for the system to move from C to D, the heat that is lost during the operation of the heat engine, it is transferred to the low temperature reservoir. So the heat that is lost is transferred to the low temperature reservoir. So this reservoir is of the low temperature. Now what essentially we are doing here is, in order to ensure that, like the heat engine, there is not much change in the internal energy of the system, we bring this system back from D to A by compressing the system. So essentially, in case of Carnot cycle, we are representing the operation of the heat engine. There are two characteristic features of the heat engine that are represented in the Carnot cycle. One is the heat transfer, both the heat input and the heat that is lost. See, both are included in the Carnot cycle. Secondly, during the operation of the heat engine, since we have quantified the heat that is lost, we have exactly know how much of the heat that is lost, there is not much change in the internal energy of the heat engine. So in order to ensure that there is no change in the internal energy of the heat engine, even though the system naturally stops at state D, we force it to a point A so that the change in the overall internal energy is 0, because we have started at A and we have reached again back at A by following a specific path. And since U, the internal energy, is a state variable, and we have started at A and ended up with A, this internal energy, similar to that of the heat engine, even in the Carnot cycle, is 0. So essentially we now have two different expressions for the efficiency of the operation of a heat engine. One that is related to that of the heat transfer, which is rather arrived at by considering the first law of thermodynamics. The second is by defining, so in this, for this expression, what we essentially considered was just the first law of thermodynamics. In order to arrive at this expression, I mean this expression is not rather straightforward to arrive at, we made the canonical description of the work done, and we made several we rather invoked several relations between pressure, temperature and volume, and finally arrived at this relation. Now in order to make our subsequent discussion quite easier, we will refer to this Q input as Q1 and the Q output, or the Q that is lost, the heat that is lost. So heat input as Q1, the heat that is lost as Q2. And similarly, the temperature of the reservoir that allows for the heat transfer into the system as T1, and the temperature of the reservoir that allows for the heat transfer from the system as T2. So now with this rather change in the nomenclature or the change in the symbol, the efficiency can be expressed as Q1 minus Q2 by Q1, which is equivalent to, because of this description here, T1 minus T2 by T1. So we have high temperatures at the denominator, heat input at the denominator. So Q1 is R at the denominator, just for my verification at least. So now on the other hand, you have the subtraction, the difference between the heat input and the heat input output at the numerator, so Q1 minus Q2, and the high temperature reservoir and the low temperature reservoir at the numerator, so you have T1 minus T2. Now essentially we can work on this relation, this equivalency here, and try to relate the temperature to that of the heat transfer that occurs. So essentially what we are trying to do is, we are trying to relate the heat transfer to that of the temperature of the reservoir. So because we have a system that is operating similar to that of the heat engine, now we have two different considerations, the heat transfer and the heat of the reservoir. So we are trying to relate these two, the system, the heat transfer with the system and the temperature of the reservoir, in order to arrive at a relation. So essentially we will begin with this expression here. So Q1 minus Q2 by Q1 and T1 minus T2 by T1. So this here can be expressed as, so you can write it as Q1 by Q1, Q2 minus Q1. So you are just splitting this expression, and ultimately you will end up with 1 minus Q2 by Q1. Now the same operation can be done for or performed for the temperature expression here. So ultimately you end up with an expression like Q2 minus Q1 and 1 minus T2 minus T1. So what essentially we can do is these can be removed, and what you would end up having is Q2 by T2 is equal to Q1 by T1. So what essentially we have is the ratio of the heat that is removed from the system to that of the temperature of the reservoir to which the removed heat flows into, and we have is equal to that of the ratio of the heat that is fed into the system and the temperature from which that heat flows. So we will express this, or if you try to illustrate it. So what you essentially have is you have a reservoir from which the heat flows. So reservoir T1 from which the heat flows. So you have considered both the temperature of the reservoir and the heat flow. So this is the system you have, and so this is our system. And from the system, what we essentially have done is we have the heat is removed and it is sent into a reservoir that is held at T2. So this is the event that is happening. Now essentially we have a temperature or a heat that is fed into the system from a reservoir of a specific temperature, and the heat, a specific amount of heat that is removed from the system and it's fed into a specific reservoir. And we see that this relation, this ratio of the heat that is fed into the system and the reservoir from which it is being fed, that ratio is equal to the heat that is removed from the system and the temperature of the reservoir to which it is fed into. So essentially what we end up having is this Q1 by T1 minus Q2 by T2 is equal to 0. So essentially what we observe is when you bring this term here and express it, or bring this term here, and we arrive at this expression that the heat transfer to the system from a specific reservoir is equal to the heat that is lost to another reservoir that is held at the low temperature. And if you relate this operation to that of the Carnot cycle we have, so we have already considered this Carnot cycle. So here the Q in is nothing but the heat input, and the Q out is nothing but the heat output, and you have the temperature, associated temperature of Ti, which is equal to T1, and the T low, which is equal to T2. So essentially what we have is this ratio of the heat transfer and the associated temperature of the reservoir is equal to the heat that is let out by the system and the associated temperature of the reservoir. And if you look closely, we observe that this heat transfer, because of this heat transfer, when you consider this heat transfer, what you essentially have is an equivalency between the heat transfer and the temperature of the reservoir, and ultimately in the Carnot cycle you end up with the position wherein you have started. So essentially what you have is, even though we consider this cycle here, there is a heat transfer from a specific reservoir and there is a heat that is transferred from the system. So heat transfer into the system from a specific reservoir and heat transfer from the system from a specific to a specific reservoir. Then even though here we have represented it as a sequential manner, if you go back to the Carnot cycle, here whatever changes happens between B and B to C and A to D, that cancels out because there is a change in the internal energy and it cancels out with each other. If you consider just the heat transfer, you go back to the initial state A. So essentially what we have is this Carnot cycle. If you could recollect, we begin here, we move here to C and D and finally A. So the heat transfer is confined to AB and CD alone. So the heat transfer is confined to AB and CD alone. In BC and DA, so this is the reason we insisted on describing these processes as non-adiabatic isothermal and adiabatic non-isothermal. So from AB it is non-adiabatic but isothermal, from BC it is non-adiabatic, or rather it is adiabatic and non-isothermal. So when you consider the change in the state of the system from B, C and D, A, what you essentially have is the change in the temperature and also the corresponding change in the internal energy. However, because of the direction of the flow, since that the overall change in the internal energy should be zero, the internal energy change when the system moves from B to C cancels out the internal energy change when the system moves from D to A, such that the overall change in the internal energy is zero. So therefore, whatever change is occurring that particularly in relation to the heat transfer, as we have considered here, is occurring when the system moves from A to B and C to D. So whatever change that is introduced into the system because of the heat transfer, it occurs when you consider the change in the state of the system from A to B and C to D. Now the other way of putting it is like whenever there is a heat transfer, be it into the system or be it out of the system, there is a correspective change in the state of the system. So corresponding work, an equal amount of work is done by the system. So the work done is largely associated, and the corresponding work done with respect to heat transfer is associated with A, B and C, D. So if you focus, we are just considering the work done by the heat transfer alone. If you focus just the work done by the heat transfer alone, this Carnot cycle can be expressed as something like this. We can get rid of the transition from B to C and D to A because there is no heat transfer that is occurring. The heat transfer is exclusively associated with A to B, and we have considered the heat transfer, and we are exclusively discussing on the heat transfer and the temperature of the reservoir. So both these parameters are largely associated with the transition of the system from state A to state B and state C to state D. So the transition from B to C and D to A, they do not involve any heat transfer and they are not associated with any other, or they are not directly involved with the temperature of the reservoir. So essentially this allows us to rather simplify the Carnot cycle into the one here. So this Carnot cycle, because of our consideration of the heat transfer and the temperature, can be expressed in this simplistic manner, wherein, so this here is the volume, wherein you have your starting point and you have your ending point for the feed, that is Q1, and from B, when you remove the heat, that is Q2, the system goes back to the state A. So essentially you have a reservoir that is held at temperature T1, and from that the heat is transferred to the system, and therefore the system moves from state A to state B. Now a heat Q2 is removed from the system when the system is at B2, and it is sent to a reservoir that is held at temperature T2, and because of this removal of heat, the system then moves back from B to A. So essentially what we have here is a cyclic process. So let me repeat, we began our discussion with the Carnot cycle. From the Carnot cycle we arrived at an expression for the efficiency. So we have a canonical description of efficiency that is described here, or that is mentioned here. We arrived at this description of the efficiency based on our Carnot cycle. We related these two and we arrived at an expression something like this. So this expression, it just relates the heat transfer and the temperature associated with the reservoir. So in order to describe a change in the state of the system that includes the heat transfer and the temperature of the reservoir, we just focused on the change of the state of the system wherein the heat transfer occurs. So we have the change in the state of the system from A to B and C to D when, so these are the only change in the states where the heat transfer occurs. So when you consider only those change in the state, we saw that whatever changes that is brought by the input of the heat transfer, or the input of the heat Q1 from the reservoir at temperature T1 is equal to the changes that is occurred by the output, the loss of heat, that is Q2, to a reservoir at T2. So because of this relation here, we are able to simplify the Carnot cycle into a simple change in the state, something like this. The reason we are able to do this is primarily because whatever change that is brought about by the transfer, the feeding in of heat from the reservoir at T1 and the loss of heat Q2 to the reservoir at T2, since they are equal, we are able to simplify this. So essentially, the change that is brought about to the system at A because of this heat transfer Q1 is B, and the change that is brought about by the heat transfer T2 to the reservoir Q2 to the reservoir T2 is back, or it reaches is equal, and therefore it reaches back to A. So essentially what we now have is a simple cyclic reaction. So we start at a point and you feed in and heat from a specific reservoir, you reach a point. And now from that point, what you are essentially doing is you are removing a specific amount of heat and sending it to a specific reservoir, and you observe that both these ratios are equal, and these changes that are brought about then go back to its original state. So there is a change that is brought about by the heat transfer from a reservoir, and that is described by this relation here, this ratio here, and this change is equivalent to that of the heat that is transferred to a low temperature reservoir that is mentioned here. Since both these are equal, so the state that we start from, even though we move away because of the transfer of heat, a specific transfer of heat, since after reaching a specific state, that is B, a portion of the heat is removed and transferred to Q2, and since this ratio is equivalent to that of the ratio that is associated with the heat input, the system then goes back to A. So essentially what we have is, we have arrived at a cyclic process wherein the system gets back to its initial state by giving out or by letting out some amount of heat energy to that of the reservoir. Now essentially this process, if you consider in terms of the heat engine, what you have is, now we have arrived at a cyclic process. We have arrived at the cyclic process primarily because we are able to relate or equate the heat input to that of the heat output. So whatever change that has occurred by the heat input is equal to that of the change that is occurred by the heat output. So heat Q1 is the heat input. The change that is occurred by the heat input to that, so whatever change that is occurred by the heat input Q1, it is described by Q1 by T1, and whatever change that is occurred by the heat output Q2 is nothing but Q2 by T2. Now since these are equal, what this means is that the change in the system, the state of the system gets reversed. So whenever there is a heat input Q1, there is a change in the state of the system. Whenever there is a loss of heat Q2, this change is reversed back to A. So what essentially we have is, we have a cyclic process, and this cyclic process is also reversible because we started at a point, we went to a different point. We started at a state, we went to a different state, and from that state, when we lose a specific amount of heat, we got back to its original state. So therefore, what essentially we have is, what this relation helps us understand is, this relation, it helps us understand that when this equivalency is satisfied, what we essentially have is a change in the state of the system that is both cyclic and also reversible. Now one way of understanding it, so this understanding is based on the change that is associated with the heat input, that is described by this ratio here, and the change that is associated with the heat output, that is described by the ratio here. Since they are equal, so wherever we started, we ended at that point. Now one other way of understanding is by considering the operation of the heat engine. So you feed in a heat input Q1, and the heat engine does a specific amount of work. And now essentially what you are doing is, and the heat engine is operating at temperature T1 and does a specific amount of work. Now when you change the state of the temperature, or change the temperature of the heat engine to T2 and remove a specific amount of heat Q2 from it, then the heat engine now is able to produce the work that was done by the Q1 at temperature T1. So we have seen that the change in the state of the system can be described by, or whatever change that is brought about by the heat input can be described in relation to the temperature of the reservoir by taking the ratio of the heat input and the associated temperature. And when there is a loss of heat to a specific reservoir and including the temperature of the reservoir, you will be able to show that this change that is associated with this heat input and the temperature of the reservoir is both cyclic and reversible. Now what we are essentially trying to do is we are trying to make sense of this cyclic and reversible reaction in the operation of the heat engine. So the way we can do that is, if you feed in a heat input and the heat engine is operating at a temperature of T1, then a specific amount of work is done by the heat engine. Now we allow the heat engine to reach the temperature T2 and remove the heat Q2 from it. And when we remove the heat Q2 from it, what essentially the heat engine would do is it will go back to its initial state. Or to put it even more in a simpler manner, let us assume that we have a combination of a heat engine and a reverse heat engine. Now you feed in, so this heat engine is at temperature T1, you feed in or you input a heat of Q1 and there is a work done by the heat engine. Now we have a reverse heat engine that is operating at T2 and you feed in the work W for the reverse heat engine. So whatever the work done by the heat engine, you feed it as an input for the reverse heat engine that is held at temperature T2. Now when you measure the heat that is produced by the reverse heat engine, it will be equal to Q2. So what you essentially have is the work done by a specific heat engine can be fed into another heat engine operating at a different temperature, and a heat that is related to or that is associated with the specific temperature, operating temperature, can be arrived at. And now when you take its ratio, so these ratios will be equal considering when this efficiency is equal. So essentially this relation here helps us understand that whenever you have a cyclic and a reversible reaction, then you can bring this term over here, then the summation of the heat transfer and the associated temperature is 0. So we have seen that this relation which we arrived through the relating the efficiency, we were able to show that this relation holds true for cyclic and reversible reaction. Now from this relation, when you arrive at this expression here, what essentially you are doing is you are summing up the heat transfer and the associated temperature. The reason why I am saying summing up is because this expression here can be expressed as Q1 T1 plus Q2 T2, and the minus sign here is because of the convention, and the convention meaning the Q2 heat is not, unlike Q1, it is not fed into the system but it is removed from the system, so therefore it is negative, and the summation here is equal to 0. So meaning when you sum both the heat transfer and the associated temperature for a cyclic and a reversible process, it will be equal to 0. Now this here is not a cyclic process. It is not here, even though it does not appear to be a cyclic process, when you consider this relation, when you consider or relate this operation of the heat engine to that of the equivalency here, you would note that whatever heat you feed into the system which has converted into work, as when you feed that work into the reverse heat engine, you arrive at an expression that those are equivalent. So it is similar to if you, instead of considering the associated temperature, instead of considering the reservoir, if you assume the operation of the heat engine and the reverse heat engine, and if you consider just the heat input and the work done, what essentially we have is whatever heat is being fed into the heat engine, is getting removed or it is getting extracted from the reverse heat engine. So that is a simplistic way of considering how this process is cyclic and reversible. So again, one way of understanding cyclic and reversible is by considering this expression here, this expression alone, and this would be purely a mathematical way of understanding it. Now when you want to attribute it or when you want to understand it from a physical standpoint, then we need to consider the operation of an heat engine and a reverse heat engine. So whatever change in the state that is brought about by the heat engine is being reversed by the reverse heat engine when the same amount of work is being fed in. So you are essentially feeding in the same amount of work, and whatever change in the state that is brought about by the feeding in of the heat input, it's being reversed by the amount of work that is released, and that is what this expression states. So there are two ways that we can arrive at the understanding of cyclic and the reversible process. One is purely the numerical way. We have arrived at a critical expression from the operation of the Carnot cycle. By manipulating that expression, we arrive at an equivalent expression, something like this. This will help us understand that now this is the characteristic expression that states the cyclic and the reversible process. The one other way of imagining is, the one other way of arriving at this expression is by considering the combined operation of the heat engine and the reverse heat engine. You feed in some heat, so these are operating at two different temperatures. You feed in some heat, there is a work done, and you feed in that work done to a reverse heat engine. You arrive at a different or this reverse heat engine produces a specific form of or specific portion of the heat, and when you relate it to the temperature in which the heat engine and the reverse heat engine are operating, then you will observe an equivalency. So essentially then what you have created is the reverse cycle or a reversible cycle process. So when you have such a cyclic and a reversible process, then the summation of the heat transfer and the associated temperature is 0. Now all that we have considered here is just two steps. So in all our examples, so when you consider just the numerical or the mathematical expression of it, we have considered from state A to state B and from state B to back to state A. So we have considered just one step process. There is one heat input, so that is Q1, and there is one heat output, that is Q2. So for this cyclic reaction that involves heat engine, we saw the summation of the heat input and the heat input output along with the corresponding temperature is 0. Now, irrespective of the number of steps that is involved, even if you increase, now if you consider this to be, or if you consider a cycle wherein instead of just from A to B, you have several other steps. You have steps that include numerous, or you have a path that include numerous stopping points, numerous steps, but nevertheless you end up where you started with. It is a cyclic process and you end up where you started with. So essentially, even though numerous steps are involved, what we have is again a cyclic and a reversible reaction. It is possible for us to get back to our initial state. So in that case, this expression still holds true. So in that case, then a generalized way. So what we are now considering is not a simple cyclic reaction, but rather a convoluted cyclic reaction. So instead of having one heat engine and one reverse heat engine operating, we can have a series of heat engine and a series of reverse heat engine, each contributing to a specific work, W1, W2, and so on and so forth. But all these works, when fed into the reverse heat engine, they bring about they reverse back the system to its original state. Then what we end up having is a complex cyclic reversible process. And in that complex cyclic reversible process, this expression still holds true. So that means a generalized way of writing it would be something like this, wherein you have introduced a variable I and you consider this ratio Qi by Ti, which is equal to 0. So the heat transfer and the associated temperature, the ratio of the heat transfer and the associated temperature for this heat transfer, and the summation of it for the cyclic and the reversible process is 0. Now here we have considered the cyclic process, and if we consider a reversible process that involves a complex steps, this ratio, the summation of this ratio, again when you appropriately include the convention, the summation of this ratio is 0. So essentially what we have is we began with a description of the efficiency. From that we arrived at the relation, and this expression for the efficiency we got that from the operation of the Carnot cycle, and from that we arrived at a relation that is characteristic of that characterizes a cyclic and reversible reaction. And this is rather a straightforward cyclic and reversible reaction. We wanted to have a generalized expression for it, wherein you're not just involved in the state of the system from one state to another, but several change in the state of the system occurs. So in that case, when you have a system experiencing several change in the state of the system, but still it ultimately reaches to its starting point, still the entire process is reversible, then the generalized way of expressing a cyclic and reversible process is something like this. So essentially we began with a Carnot cycle. We began with a cyclic process. We arrived at an expression and characteristic expression, and that expression we generalized it, and this generalized expression is now what we will be using to describe a reversible process. Now we started with a simplistic system, a simplistic cycle. We saw that this cycle helped us arrive at a specific expression, and this expression now we generalized it, and since we started with a simple cyclic process, we started with a simple reversible process, arrived at the expression, extended to generalized expression. Now this generalized expression will now act as our criteria for describing a reversible process. So when you define a reversible process, when you have a reversible process in your hand, this condition should hold true, because this condition is arrived for the reversible cycle, and this condition should hold true whenever you have a reversible process. Now what you essentially have in this case here is you have several steps that are involved, and you have, for each of these steps you are considering the heat transfer and the associated temperature, and the sum of it is 0. Now when you reduce the number of steps, when you make these number of steps smaller and smaller, you can express this, or you can arrive at this in even you can express this in a more generalized manner by including a closed integral and expressing it as the heat transferred and the associated temperature is 0. So what you are doing is, you started with a simplistic cyclic and reversible process, arrived at an expression, generalized it by considering numerous number of steps, assuming that there are numerous number of steps that are involved. So that gave us this expression here, a generalized one. Now what we are considering is, we are minimizing the width of the step, and we are expressing the summation in the form of a closed integral. So again, the fundamental description of the integral is summation, but here what we have is a cyclic and a reversible process. We are getting back to the state where we started in, so therefore we have our closed integral, and this delta Q is the heat transfer that is involved, and T is the associated temperature is equal to 0. So now this expression is something that we have seen in the previous lecture. When we introduced the concept of entropy, this is how we described it. So the entropy, we described it as the ratio of the heat transfer to that of the temperature that is involved. Now one description that we had for the entropy is the degree of irreversibility, and here we are exclusively talking about the reversible process. So entropy is the degree of irreversibility, but we are here talking about a reversible process. So how to make sense out of this? Now when you consider each and individual step, each and individual step is an irreversible process. The whole process, the complete process is a reversible one, but each and individual step is irreversible, and this each and individual step is quantified by this term S here. And therefore, even though entropy, the definition of it still holds true, entropy still is the degree of irreversibility, entropy still is the change that is brought into the system. When you consider the overall process, since it is reversible, the overall change in the entropy is 0 for a reversible case. So the expression that we arrive at here from the relating the efficiency for the simpler case is nothing but the expression for the entropy change for a completely reversible process. So whenever you have a completely reversible process, the change in the entropy is 0. So what we essentially have here, what we have done so far is, let me recapitulate everything we have done in this lecture, because there are both numerical concepts, or rather purely theoretical concepts, that are involved and which can be related to the operation of the heat engine. Nevertheless, these are some fundamental concepts that will help you understand, that will help us understand or relate the second law to the phase changes that we are interested in. So therefore, or the working or the behavior of the entire universe that surrounds us. So therefore, let us spend some more time in understanding what we have done so far. So we began with the Carnot cycle. We arrived at, or we considered, or we described the efficiency in two different manners. Now, since our starting point was a Carnot cycle, a simple cycle, we were able to arrive at an expression for a cyclic and a reversible process. Now, that expression we generalized it by considering numerous steps, and even we refined that expression by including a closed integral. Now, when you focus on this expression, when you consider the terms, the parameters that are involved in the expression, we saw that, so this is delta, a minor change, or the heat transfer that is involved. So we see that these parameters it relate to a thermodynamic variable that we are familiar with, and that thermodynamic variable is nothing but the entropy. Now what we observe is, even though the change in the entropy, it relates to the degree of irreversibility for each step, even though there is some amount of irreversibility that is involved, since we are considering the overall reversible process, when you consider the overall change in the entropy, it is equal to 0 for a reversible cycle. So even though there is the description of the entropy is the degree of irreversibility, it is possible for us to estimate the change in the entropy for an overall reversible cycle, and that is equal to 0. So what we essentially have is, we have two different change in entropy associated with a process. If the process is rather reversible, then there is no change in the entropy. When the process is reversible, there is no change in the entropy. Now we are interested in the irreversible process, the spontaneous process, and we would like to know how the change in the entropy occurs when you have an irreversible or a spontaneous process. Now the reason we have this criteria, the reason the second law of thermodynamics is primary, or it is important, because again all these criteria we were able to arrive at through the second law of thermodynamics, through the Carnot cycle that helped us describe the second law of thermodynamics. Now the reason this is vital, because whenever you claim that, so there are several reversible chemical reaction that surrounds us. So whenever you claim that this is a reversible process and this is a reversible chemical reaction, then this criteria should satisfy. Now this criteria meaning that the overall change in the entropy during the entire process, not just the individual step but the entire process, is 0, and only when this condition is satisfied, the process is reversible. If it is not satisfied, then the process is not reversible. Now based on this, so this we arrived at by considering the working of the Carnot cycle. This expression here, the fundamental way of expressing this was the Q1 by T1 plus minus of Q2 by T2. So this is the fundamental expression that we arrived from the Carnot cycle that ultimately helped us reach this expression here, helped us reach this very basic criteria here that indicates that there is no change in the entropy or the entropy. So whenever we do not have any change in the entropy, it means for a reversible process the entropy remains constant. Whenever you have a reversible process, the entropy remains constant. There is no change in the entropy. So that is what this expression here. So this expression, this criteria here, we arrived from this relation, this fundamental relation that we got from the operation of the Carnot cycle. Now when you consider this change in the so when you consider this expression here and we consider the simplistic cyclic case that we have assumed, so you have a system at A and your system reaches B because of the heat transfer Q1 from the reservoir T1, and now you have a heat transfer from the system which is at point B or state B to a reservoir at T2 and reaches A. So that is a heat transfer Q2 to a reservoir T2, and the system goes back to A. So essentially you arrive at this expression here. So now the entropy change when the system moves from A to B is expressed by this relation Q1 by T1. So the entropy change, the change in the entropy when the system moves from A to B is given by this relation here. Now similarly, the entropy change that the system exhibits when the system moves from B to A is given by Q2 by Q1, and this is negative because the heat is removed. Now essentially what you have is, you have the change in the entropy cancelling out each other, thereby fulfilling the criteria for the reversible process. So this is what we are validating, or we are ensuring that just by considering this simple cyclic case here, we are able to arrive at this, or this simple reversible process here, A to B from B to C, we are able to arrive at this relation here, because when you sum this up, the overall change for the reversible process will be dSAB plus dSBA, and this, because of this expression here, you end up having no change in the overall entropy for the reversible process. So this reversible entropy, or the change in the entropy for the reversible process, is 0, and this can be proved by considering the simplistic case here. Now in the next lecture we will try to consider or see how the entropy changes when you have an irreversible and a spontaneous process. How will the entropy of the overall process change when the process is irreversible, or it is governed by the system spontaneously as it tries to reach a new equilibrium. So with this, I would like to wind this lecture up, and we will see ourselves in the next lecture, wherein we will focus more on entropy and the irreversible process. Goodbye.